I normally would have started a day ago. Guys, once should be enough, twice should be more than enough. This is the third time. So this is not a difficult chapter, but it's a bit of a change. So just bear with me, and as you have questions, please raise your hand so I can address them as we go along, because I have noticed that unforced errors kind of, go up when students start to do this third chapter, which is projectile motion, essentially kinematics, the same thing that we were doing, but in 2 dimensions. And it's the gateway to getting to Newton's laws, which is a total change in terms of how we do things, because all the techniques that you have learned so far will be broadened up when you get to Newton's law. But before that, this is an important intermediate chapter, and so it's important that you don't have any weaknesses that remain as you go through this chapter. So I will assign the next problem set, which will be primarily on the stuff I'm going to do today, and a little bit of what I've already done, and a little bit of what I'm going to do on Tuesday. So the next problem set will be a transitional set with respect to what you have done so far. So just allocate time carefully. You don't want to fall behind in any of the sets, and most certainly the next set.
When will this set be due?
All of them are due the following Monday. So the one that's currently on is due next Monday, and the one that will be assigned next Monday due the following Monday. So you generally have a 3 or 4 day lag in most cases from when the material is done to when the work is getting done by you guys. Now, on rare occasions, it can happen that you'll be slightly ahead of the class. I try to avoid that, but there are times when that does happen for completely uncontrolled circumstances, which is one reason why I remind the students to look at the YouTube lectures. One reason why the YouTube lectures are there are basically because nobody falls behind. I'll have travels, for example. Thus far, I have not been traveling. Some travels become unavoidable, and I don't want the class to fall behind because we don't have that luxury. So then I would have the YouTube lectures going on, and we would do everything else in class, but you won't have my regular lecture. It will be on YouTube. So but anyway, to answer your question, we'll be a little bit ahead of the homework schedule. Okay. All right. So this chapter, this is chapter 3 in your book, deals with projectiles. So this is not a difficult chapter. So let me just give you an idea of what projectiles really are. So we would take the simplest case of what one can call half a projectile. So we'll first do half a projectile, and you will see that doing half a projectile is actually good enough to literally work out the full projectile. So that's why I want to start with a simpler case of half a projectile. So suppose you are under attack. So this is some kind of a fort. Here you are, defending your fort, and you have a cannon that is pointing horizontally. Well, this is not exactly horizontal, but I'll make it horizontal. So there you are trying to do this, and the reason why you're busy with the cannon is because there are ships that are trying to come to attack you. Whatever. And so you want to defend your fort. And unluckily, there is more than one ship that is trying to attack you. And let's say this is an even bigger ship. and they also have cannons. Excepting being in your castle, you can see them first. So now you have a problem. You're trying to figure out how to hit both of these guys simultaneously. So first question is, can that be done with the way you have the cannon aligned? You know that cannons can't be easily moved. They are very heavy and very inconvenient. Can that be done? Can you hit both the ships simultaneously? What do you think? Who thinks that it is possible? You guys are a pessimistic bunch. Actually, it is possible to hit both of them. So let's see. So we will do some basic kinematics just like we have been doing. Excepting now, we have the motion that's going to be kind of like that, right? So this is what we mean by projectile. And I said half a projectile, because a full projectile obviously would be like this, right? That will be a full projectile. So we are not doing that yet. We are doing half a projectile. So let's first do half a projectile. So in this case, you want to do this, and you want to keep this horizontal, which basically means that you should have a velocity initially in this direction, and this is the initial velocity, so we call it v0, just like before. But because this is the horizontal direction, and normally we would take an x like this and a y like that, I would call this v0 of x. Now the important thing here is, because the cannon is horizontal, what would be the vertical velocity of the cannon as it leaves the gun itself? You have fired it horizontally. So what would the vertical velocity? Huh? What? Well, yes, it'll be 0, because you haven't given it any vertical velocity, right? So the vertical velocity v0y, so initial, hence v0y is going to be 0. Okay? And obviously we know that there is acceleration due to gravity, so there is going to be minus 9.8 meters per second square. And let's say there is a certain height from which it is being shot, and we can call this height y for now. So we need to find out what's going on with this cannon, and let's just poke around with some basic kinematics. So the first thing that we can already see is that there are two pieces to the motion. There is a vertical piece to the motion, and there is a horizontal piece to the motion. Now, I have already taught you that you should be writing out all the kinematic equations and so on and so forth. So if you think about the kinematic equations, then, well, first record what you know. Let's say you do have a v0x, and let's define this v0x to be v0 itself. This is vertical. A v0y to be 0, and v0x to be v0 itself. We call it v0. There should be an acceleration along y. I would call it a sub y, and this I would be describing by g, right? But g is downward, so just to be clear, I would write it like this. Now, along the horizontal direction, there is no acceleration because the cannon has been fired, and if we ignore air resistance, we shouldn't have any deceleration. Yes?
So, since the ball usually ends up like going downward, why wouldn't it have a velocity? It's not traveling in a straight line.
It does have a velocity, but what velocity do you mean?
Well, like, wouldn't it have velocity at a certain point?
Yes. Yes, it will have a velocity which will be both vertical and horizontal as it develops in time. But initially when you fire, the velocity is only horizontal. Okay? There is nothing vertical. Clear? Okay. Any other question? Okay. So A sub x then is going to be 0 because there is no velocity if we ignore air resistance in the horizontal direction. So, and then there is, that's basically all we got pretty much right now. So let's say what we can do with it. Let me just record these things and see what we can do with it. Well, when you see this, the first thing that you notice, given that there is a y, is you can actually calculate the vertical motion very easily, because you know v0y is 0, acceleration ay is minus g, and let's say the height itself is y. So we should be able to write, let's say, y itself is 1/2 minus g itself times a t squared. So therefore, I should be able to find a relationship between the fall time of the ball. This is the vertical fall time and y. And so therefore, y should also be negative because it's going downward. So the two minus signs take care of each other. I can forget about the magnitude of g here. So I can simply write it as 2y over g square root. And it's understood that we are taking the positive root, because the negative root wouldn't make any sense. So now you see, this is the time taken by the ball to fall and hit the ground. Now obviously, the ball is a whole. The ball has two pieces to its motion. There's the vertical motion, and it also has the horizontal motion. So the very important thing to note now is that the same time controls how far out it goes horizontally, because that time is actually set by this quantity here. So once you set your y, that time is already set. You have really no control over it as long as you are on Earth and you have a fixed g. So therefore your horizontal motion is now going to be controlled by this time t. So let's say the horizontal motion is such that you are traveling a distance x horizontally. So in other words, the distance here, let me, so let's say I want to hit this ship, and the distance from here to here, I can draw it here, doesn't matter, it's actually my x. Let me just this out a little bit. Okay. So it will then turn out that this x is going to be v0x times t. You don't have a choice, because that will be the time involved in the horizontal motion, because that's completely controlled by the vertical piece of the motion. You have just separated the two out, just you would separate a vector out. And since we already know that t is square root of 2y over g, I can write it as v0x 2y over g square root. Does anyone have any idea as to what that equation is for? This equation. You have an x on the left side and the square root of y on the right side. What does that equation describe? What kind of a curve does the equation describe? Very good. It's a parabola. Because you can write x as v0x times 2y over g, just like you have done, and then you can square both sides. And immediately what you get is x squared is equal to v0x squared, whatever the value of this may be, times 2y over g. So you see, for every value of y, you could have two values of x. Although in this case, because we are doing half a projectile, for every value of y, we are only going to get one value of x. But what I'm trying to tell you is that, number one, this curve that the bullet will trace, or the cannon will trace as it goes down, is going to be a parabola. That obviously is your x, and that's your y, right? However, I also told you in the very beginning, that's half a projectile. If you want to do a full projectile, it's very simple, because the equation already is valid for the full projectile. It already tells you that x can be positive or negative. So in other words, you can have a very similar kind of motion which can start here and go that way, and the relation between x and y will be just exactly the same as what we have obtained here. I'll come to that. Let's not get too carried away, but let's get back to our cannon problem. So now you see the fall time is the same. So regardless of how fast I fire the cannon, because v0y is 0, the fall time of the cannon is set by 2y over g, square root of 2y over g. I can't control that. So in other words, if you were to make two shots, or if you have two cannons, one shot you make, let's say, with v0x, where v0x is such that the x that you will get in the fall time is going to hit the first ship, and the second cannon is such that the v0x is adjusted, again in the same fall time, such that you hit another x prime, whatever the second ship, let's say it's twice the distance away, you just basically have to fire at twice the velocity, and you will be hitting both the ships. Okay? So if you think about it, in this problem, it is indeed possible to hit both the ships, provided you can make two firings at just the right velocities that they'll reach the range, that they'll reach the x. The y is fixed. Any questions so far? No? All right, let's move on. So the point, therefore, that you want to remember with regard to these problems is that the fall time is very important, or the rise time is very important, depending upon how it's been fired. In this case, it's been fired upward, so there'll be a rise time. So this rise time controls how far out it will go. Of course, how it's fired depends, therefore, on the velocity used and the angle at which it's been fired in this case. So let's do a simple half projectile problem. Very simple. Suppose this is a swimming pool, and suppose here you are, that you want to jump into the pool, and you want to clear this ledge. So let's say the height of this is 10 meters, so it's quite high, and let's say this ledge is 2 meters wide. So this is a very simple projectile problem. The question may be what velocity that you must have while running such that you can clear the ledge. If you are running too slowly, you might end up on the ledge, and that won't be a lot of fun. But if you run sufficiently fast, you will end up in the pool, you will clear the ledge. And if you have just the right velocity, you will barely clear the ledge. That's what we are looking for. What is the right velocity such that I can barely clear the ledge? I know this is 10 meters, I know that's 2 meters, I don't know anything else other than the fact that you want to go horizontal. That's all I know. So question may be, what must be your horizontal velocity v0x such that you'll just clear the ledge? All right? That's what we're after. So again, just like we did, I can already see that v0y is going to be 0 because there is no vertical velocity. I'm just moving horizontally, or running horizontally. The acceleration a along the y direction, you see now I'm writing ay and ax, just so that I don't make a mistake. The acceleration is only in the vertical direction, there is no acceleration in the horizontal direction. So this is clearly going to be minus g. By the way, you can also write it as minus 9.80 instead of putting a mod and all. I don't have a problem with that. as long as you know what you're doing with respect to this. So we also want to find out what is the fall time, and I know that the height through which it falls, y, in this case is minus 10.0 meters, because I would take this to be my y equal to 0 level. And the question is, how long does it take? So again, just like before, I would use the same formula because I have a y and a t, which means that in this case, v0y being 0, it's going to be 1/2 ay times t square. That then would mean that minus 10.0 meters is equal to half times minus 9.80 meters per second square times t square. So therefore, I should be able to write this t square as basically 20, because 2 times 10 is 20. This would be in meters. And downstairs, I should be able to write 9.80 meters per second square. So to make life easy, let me approximate that as 10.0, as 20.0 on the top and 10.0 on the bottom, second square, which means, since this is 2, my t would be, my t would be approximately equal to square root of 2 seconds, which is basically equal to 1.4 or so seconds. So now that I know the t, which is always the most important thing, I can actually figure out what his velocity must be so that he can clear the distance. So let's say now the x that I have is 2.0 meters, right? Or 2.00, whatever you want. You can make it 2.00 meters. And this is equal to v0x. I don't know what v0x is. This is something I'm after. And the time itself is square root of 2 seconds. So clearly, it is trivial now to see that v0x must be approximately square root of 2 seconds for you to be able to clear it, meters per second, sorry. Which means that this should be approximately 1.4 meters per second. So as long as you're running with 1.4 meter per second velocity, you should be able to clear the ledge, right? It's a very simple problem, but nevertheless it makes a very important point that the way to do these problems is to first get a handle on the time of fall. So there is another point I want to show with regard to the equation for the parabola that we discussed. So as far as the equation for the parabola is concerned, I told you that x squared is v0 x squared times 2y over g. So one of the things that will happen is as I raise v0x, everything else remaining the same, as I raise v0x, obviously the distance traveled horizontally would go up. So if g goes to 0, suppose you are on the moon where g is very tiny, Mars is not such a small g, much less than Earth though. If g were to go to 0, then almost any v0x will actually make this range very large. So if g were to go to 0, or let's say v0x were to become extremely large, then it tells you that x itself will become extremely large. So that's an interesting problem. So in other words, this velocity is the only thing that controls how far out you can go. Now, one of the problems that was brought up is the calculation of these things can be quite interesting and quite tricky. So let's briefly analyze the actual motion of the cannon or the person or the particle in the projectile. So I already told you that it'll be a parabolic trajectory like this. So let's try to understand what are the velocity components in this parabolic trajectory. So clearly when it starts out here, in this case and also in that case, I've already said that all you have is just a horizontal velocity, and that is v0x. I've said that there is no vertical velocity v0y. So let's stick with that for simplicity. So you see, I have also told you that there is no acceleration along x. What does that mean? That means it doesn't matter which point you take on this trajectory, your v0x remains exactly the same. So if I were to draw the vectors for v0x, it will remain exactly the same all through its trajectory, because there is no acceleration along the x direction. What changes then? Why is it falling? Well, naturally it's falling because the y part is growing, because you have an ay, which is your acceleration due to gravity. So initially, this is 0, so it starts out going horizontal. Then as time passes, this thing becomes larger. And as this grows, the projectile gets progressively pulled down. So therefore, if you are asked to calculate at what angle this projectile is going to hit the ground, you already kind of know how to handle this problem. So let's analyze that very quickly. I won't do the detail of it, I'll just sketch it for you. So suppose the projectile comes in like this and hits the ground. You already know that the x velocity of the projectile remains unchanged. Whatever the initial x velocity was, that's exactly what you got. No change there. All you need to calculate is what is the y velocity. And it's the y velocity and the x velocity combined that actually sets the direction in which this thing hits the ground. So in other words, in this case, the resultant vector may be, well, I didn't draw it right, so let me make up for it. So resultant vector would be like this out here, and that is because there is a v0x which has been the same, and the v0y has grown to this magnitude, and once you combine the two vectors, that's what you're going to get. Now, how would you know what is the angle with which it's coming down? So that's something that can be tricky. And that's the reason why I'm showing it to you. Why can it be tricky? Well, the first thing that you want to make sure is you know the angle is defined with respect to what. So if nothing is said, the angle is almost always defined with respect to the positive x-axis, because this would be the positive x-axis. So this is the angle you are typically after. So if that's the angle you are after, so this is coming in like this, as long as you know this angle, you should be okay, which means basically this is a straight line, this angle. So if you know this angle, let's call this angle theta, and let's call the angle that you're after phi. So if this is theta, geometry tells you it doesn't look like it because it's a curved line. If this is theta, this is also theta. That means the phi that you will report would be 180 degrees, because the full angle here is 180 degrees minus theta. So you first find theta, and in this case you have to find what happened. This is what we are after.
Right, but
this is what we are going to calculate.
right, the ones you equated, the lower one should be the one counterclockwise.
Oh, I see. I'm sorry. Yeah, that's right. This is the theta. Yeah. The answer is right. I'm sorry. Yeah. So essentially what you have done is, so that's not the right formula. Thank you, Rance. So this is the way it's coming, right? And this is the vertical. So you know this angle. So this angle sets that angle, and then you add 90 to that to get phi. So that will be theta plus 90 degree for this one. Okay? So how would you find this theta? Well, it shouldn't be very difficult because you already know that this is your V0x and you already know that this is your V0y. So therefore you should be able to write your tan of theta. Yes, opposite is V0x, adjacent would be V0y here. So that will give you theta. So theta then would be the arctan of V0x over V0y. So that will be the angle. Yes?
The vertical component be V final y because there's gravity.
Say that again, I didn't.
Would the vertical component be VFy?
Right, you're right. I should change the notation. V final y. Yeah, you're right. V final. Yeah. So because I never changed my notation, I forgot. So this thing, as it hits the ground here, you'll have V final of y. So this is the piece you have calculated, V final of y. This one has remained the same, and it is the V final of y that is changing the theta. And once you know the theta, you simply add 90 degrees, and that will give you the phi with respect to the positive x-axis. Yes?
Would you mind going over how you got those three equations again? Because it's just kind of hard.
Sure. Which three? The angles?
Phi,
Yeah, okay, let's go over it one more time. So this thing comes in like that, right? And this is the ground level. So first thing you realize is that there is a V0x and there is a V final y. V final y is because of the accelerating motion downward, right? So then what happens is that you draw the parallelogram and you figure out what this vector is. And let's say this vector makes some angle. Then if you do this, you will find that there is a theta angle here, right? They're like, this is the angle between two lines. So this and that would be the same. So if this is theta, that is theta. So how do we calculate theta? This is how we calculate theta. Tan of theta is going to be the opposite. This is the angle, so the opposite is opposite here over the adjacent. So V0x over V final y. So tan of theta is going to be V0x over V final y. So that's how you get tan of theta, which means you can now get this angle because this angle and that angle are the same. But normally, as I said, you will define the angle at which it comes down unless you are otherwise told with respect to the positive x-axis. This is the positive x-axis. The right side is the positive x-axis. So therefore, you would add 90 degrees to that angle theta, and that's what I was calling phi. So phi is the full angle. This full angle is phi. Does that make sense? Anybody else who's lost? Okay, very good. This is always a bit tricky. In fact, I have given you a problem in the homework set that deals with it. Let's now quickly do the full projectile problem. The full projectile problem is also quite straightforward. So, in the full projectile problem, the way you consider it is that you first draw your vertical axis, then you draw, let's say, your horizontal axis, or vice versa, and you are launching the projectile at some velocity v0. Okay, this is the magnitude of the velocity. Since velocity is a vector, it will have a direction, and the direction is, as usual, defined as theta with respect to the positive x-axis. That's what we got. All right. So now what should happen is that if you draw the picture, which you must in these problems, actually in all problems in physics, if you don't draw the picture, you'll sooner or later get into trouble. You expect that there will be some kind of a trajectory like this. Now, I have not set any preset limitations on where this thing is going. In principle, it can start from a level and end up in the same level, or it can end up somewhere here or here or here or even below. And we will do all these cases as we get through projectiles, because these cases are kind of important to understand for us. As we have already learned with our cannon problem, is whenever you see a projectile problem, you break it into two pieces, the horizontal piece and the vertical piece. So in this case, the horizontal piece basically would be if you drop a perpendicular, you'll get a V0x, and V0x will be naturally V0 cosine of theta in this case, depending upon how theta is defined. Oftentimes, one would make a mistake by writing the horizontal as the vector times cosine of theta without being careful. It depends upon how theta is defined. So if theta is defined with respect to the positive x-axis, then V0x is V0 cosine theta. However, if I know this angle, then V0 cosine of theta will wind up being on the V0y. So you have to be careful. Anyway, so this is V0x, and V0y is going to be V0 naturally sine of theta, right? So, and then we have no acceleration along AX. We have an AY, and AY is minus G. And then we have to deal with stuff like how high does it go, how long does it take, and also how far does it go, what is the X. So these are typically the things we are after in a projectile problem. So I'm going to do the various calculations of a projectile problem right now. So let me just pull this up, that way you can see it. Okay. So let us calculate how high the projectile rises. How high the projectile rises. Let's call this h. So this obviously the vertical height is now h, right? So if you look at that, the vertical height will be h. Now at max height, something special will happen. What will happen? The V final of y must be 0. We have already seen that in 1D motion, if I throw something up, it goes up and comes to a stop and comes down. So at maximum height, the vertical velocity will be 0. What happens to the horizontal velocity? It remains just the same. The motion doesn't stop. The motion continues on like this. But at this point, it's only the horizontal velocity that's there. Nothing vertical is there. That's all we are recognizing. We know that V0y is V0 sine of theta. I call it theta or theta 0? Theta, okay. Acceleration I know is minus g, right? And I asked the question, what is the h? So in this problem, so we have v final, v initial, acceleration and height, which means that the only equation that we can use would be the equation which is v final y square is v0 y square minus 2 in general ay times, in this case h, so we put the sign in carefully. V final y is 0, so I'm going to make this 0. V0y is v0 square sine square theta, and then you have a minus 2 g times h, which means h, the maximum height, is going to be v0 square sine square theta divided by 2g. That's an important result. So the height will be v0 square sine square theta divided by 2g. So you can see now that if theta is 0, then you can't have anything going anywhere, right? If theta is 0, it's just going to go down. So your height will be 0. Sine of 0 is 0. If theta is 0, this is 0. That's very boring. What is the maximum value of theta? What is the value of theta for which sine is maximum? Come on. Which value of theta gives you the maximum sine? 90, right? So how can you forget the theta stuff that I told you? So if I have theta equals 0, let's see, how do I do this table? I always get confused doing these tables if I don't write. Let me write down like this. Theta and sine theta. Easier. So if theta is 0, sine of 0 is 0. If theta is 30, I already told you it's half. 45. So I already told you write it like this. Root 2 over 2. 60 is root 3 over 2. 90 is 1, right? And then if I write cosine of theta, then cosine of 0 is 1, and it goes the other way. So it will be root 3 over 2, root 2 over 2, and then cosine of 60 is half, or like that. So you should know this. I mean, this is today. I'm surprised today you are not sure about the numbers. So you can easily see now that if theta is 90 degrees, h will be the maximum in this case. Because sine of theta can't be more than 1. That's the maximum value it can have. So we can also calculate another very important quantity there. So let's do it here. And that is the total time of flight. So projectile problems can be tricky. So you first, when you do these problems, first make sure that you do a very neat and clean diagram and make sure that everything is correct. So once you have your diagram, then you figure out what it is that's being sought and sort out how you want to attack them. Make sure you break up the problem from the get-go into an x piece and a y piece. And the only thing that connects the two would be time, right? Because the original motion is being split up into a horizontal motion and a vertical motion, and what is shared between them is time, because it's one particle that's going wherever it's going. So let's say we want to calculate the time of flight. The time of flight of the full projectile. And we'll do the simplest case. The simplest case would be that the net displacement y is equal to 0. And what that means is, if you look at my figure, it takes off and returns the same height. So if this is my level from which I have fired it, it takes off from here and it returns the same level. So as far as the y-axis is concerned, it starts here at whatever value of y it is and returns there. So therefore the net displacement is y equal to 0. So since we have y and we are after time, we have only one equation that we can really use in this case, which is y is equal to v0y t plus 1/2 ay times t square. So v0y is upward, so it's v0 sine of theta, and this is t, minus g over 2, let's say. If you want, you can put a mod. Again, it's not important. And here you have 0, because it comes back to the same level. So therefore, you are left with the following scenario. This implies that g t squared divided by 2 is v0 sine theta times t. Now you have to be a little bit careful here, Right now it is a very simple thing, but sometimes this can unnecessarily cause an error. So in this equation you can see there is a t squared here on the left side and a t on the right side. So naturally our first urge would be we divide both sides by t, so then I can get rid of this t and make this into a t, right? That will be our first urge because that's the way to simplify. But there is a physical thing that you are doing when you cancel the t's. You're basically ruling out, you're taking out the case where t can be 0. Because remember, you can't divide by 0. That is prohibited in math. So when you are doing a cancellation here, you're basically dividing by t here, and you are dividing by t here such that this becomes just a t and this becomes 1. If you're going to do that, then you're basically saying that I am rejecting the t equal to 0 solution as a viable solution here. Now, why would you do that? Well, there is a physical reason for it, because if t were 0, the particle hasn't even taken off. So it is indeed a trivial case, but the equation still gives you that trivial case as an answer, and it is your job to determine if that answer makes sense. And you basically say, well, this is the trivial answer because the particle hasn't even taken off, and hence t equal to 0 is not a case that I'm interested in. So I'm only interested in when t not equal to 0. So that would then mean that t would be 2v0 sine of theta divided by g. Now be careful though, this is the time for the full flight, meaning that leaving at one level and coming back to exact same level. This is not the time if I'm leaving at one level, ending up at another level, whether it's up or whether it's below. That time will have to be calculated separately. But this is the time that is associated only with the fact that it takes off from here and goes there. Now, this time is, by the way, kind of important, because this time is associated with what is the total distance horizontally that the particle in this case has moved. And this has a name, and the name is range. And range is normally written as r. So you will find that because it's a special quantity, almost every book, including yours, derives or works out something called a range formula. And one of the tendencies that students have is whenever we see a formula which is put in a box, we realize, for obvious reasons, it's put in a box, that it must be important. And oftentimes there is a problem associated with putting that in a box, because this is a very special case. And most times in most problems, the range formula itself is not very effective unless you are dealing with a motion where it goes up and comes back to the same point. So be very careful in using the range formula in your analyses. Okay? Make sure that it's applicable. I can't tell you how many mistakes I have seen students do by knowing everything, perhaps knowing everything a bit too well, and then getting too excited because they see it's like a range calculation, and then they forget that it's not a full y equal to 0 problem like I have done here, and then they, at the end of the day, make an unnecessary mistake. So the range here is very easy to calculate. So we already know that the horizontal distance traveled is the horizontal velocity times time, because there is no acceleration in the horizontal direction. We already know that. So what is the horizontal velocity? Well, horizontal velocity is v0 cosine of theta, right? We already know that. And then we have time. Time is given by 2v0 sine of theta divided by the absolute value of g, which means that if I were to calculate the range, it will have a nice expression. I have two v0s, so it's v0 square. I will write this as 2 sine theta cos theta for reasons that will become clear in a moment. And then downstairs, I have the value of g. Now, for those of you who have not been using trig for a while, which is not unusual, there are certain things about trig that you need to know. One of the things I pointed out is sine squared theta plus cos squared theta is 1. It's an important identity that will come in quite handy for you guys regularly. Another one is cos 2 theta is 2 cos squared theta minus 1 equal to 1 minus 2 sine squared theta. These things you got to memorize. You got to know these things. And a very simple one is sine 2 theta is 2 sine theta cos theta. So therefore, I have 2 sine theta cos theta here, which means that the expression for r can be further simplified, and so r would be v0 squared over g times sine of 2 theta. So again, as I said, I will put it in a box, but be very careful as to how you use this equation. So let us see what this range really gives us. Let me go to this board. What does it tell you? So if you were to throw a ball, at what angle would you throw the ball to get the maximum range? Forget about the formula. Just tell me from your instinct. Louder. 45 degrees. So you see what happens at 45 degrees. 45 times 2 is 90. So sine of 90 is 1. I have already told you that the maximum value this guy can have is 1. So this formula tells you something that you probably know very well, that the maximum range you can possibly get in this problem, where it takes off from one height, comes back to the same height, is then simply going to be v0 squared over g. That's the maximum possible range. It is set by, in this case, by v0, and also set by theta, which is 45 degrees. So in every case, the trajectory of the ball or trajectory of something is determined by v0 and by theta. So let's see what these numbers mean. I would make a table here, call it theta here, and call it r here, because I have a formula, so I can kind of check it. So it's obvious that if theta is 0, that means you have not really thrown it, and so not surprisingly, you won't be going very far. If theta were 15 degrees, you see now you can do a little bit of work here. If theta were 15 degrees, 2 theta makes it 30 degrees. You already know that sine 30 is a half. So therefore, you'll have v0 squared over g, which is the maximum range I already gave you, multiplied by half. Because sine of 30, sine of 2 theta, theta is 15, is going to give you a half. If theta were 30 degrees, then of course it will be sine of 2 times 30, sine of 60, which is root 3 over 2. So therefore I'll wind up with root 3 over 2 times v0 squared over g. By the way, I can write it in decimal points if that makes you more comfortable, so you can actually see what's happening. And root 3 is 1.732. Don't forget that. Root 3 is 1.732. If you divide 1.732 by 2, it's 0.866 v0 squared over g. So you see the range is going up. The range will max out at 45, because 45 means sine of 45 times 2 is sine of 90, and we already have calculated this is v0 squared over g, which means 0.5, 0.866, now it becomes 1. Past 45, the opposite happens. So 60 will give you 120, in which case you'll again get root 3 over 2 v0 squared over g. and then at 90, at 75, you'll get 150, and that will actually work out to half V0 squared over G. So here this becomes 1 times V0 squared over G, and then it becomes 0.866 times V0 squared over G, and then it becomes 0.5 V0 squared over G, etc. So if I were to draw a picture, then the maximum range would be if I launch it at 45. But if I launch it at a steeper angle, you can already see what happens. It can go higher, but it'll have a shorter range. And the same thing will happen if it's launched at a smaller angle. It'll wind up with a smaller range. So therefore 45 is optimal, and that's exactly the formula it's telling you. Now that said, most times I won't ask you to calculate or work with the range formula, but I'll give you something which is a little bit, that requires a little bit more thinking than that. Now, one of the problems that I try to do in class, and I might spend a bit of time next Tuesday doing, but this is going to be a problem that I'm going to assign for next week. Now, the problem will be worked out in my notes substantially with some set of numbers. But the problem is very simple in a way. You have done the problem where somebody catches somebody, and this is very similar. Here you have, let's say, a missile being launched at some angle. At some velocity, let's say, some angle here. Question is, if you can launch a second missile that will intercept the first missile. That's the question. And the answer is, yes, that might be possible, because you can always have two projectiles launched at two different angles. For example, this can be launched with the same velocity perhaps, but at a steeper angle. And it can be made to intercept the missile at a unique time and unique point in space. So this is an interesting problem. First of all, it's an interesting problem from the standpoint of just doing the kinematics, because you obviously know that for them to meet, the x and the y positions must be the same, and they'll meet at one fixed time. Since nobody would want to launch two missiles like this at the same time just for fun, normally a missile would be launched first, and the second missile would be launched shortly thereafter. And usually there is a window within which the second missile must be launched if you must intercept. And typically that window is very tiny. So this problem actually is about the calculation of this window for a particular case. So it turns out that the way you control the window, if at all you can, would be by varying the launch angles and by varying the velocities. So the problem I'll give you will have the same velocity for both missiles. It's simpler, but you can also vary the velocities. So when you hear about stuff like, if Russia launches something, we can launch something, it is true we can. Or if we launch something, they can launch a missile which can potentially intercept us. But there is always a window, and it's a very narrow window. And this is the reason why the decisions are important, because you better be sure that if you're going to launch something that will be effective, how you do it. And if you're going to respond, then how rapid your response time must be, because if your response time is not within that window, there is absolutely no way that you're going to be able to save yourself from calamity. So this is a problem that I'm going to assign. It's a nice problem. I think you guys will be able to do it. Again, there's a blueprint of this problem in my lecture notes, and I'll post it. So let's get your stuff away, and let's go to the quiz.